Good morning, students. This is M. Prasant Raju. Stand before you to continue the classes of Wave Optics, UNIT-1, R23 Regulation, Engineering Physics. Today, we are going to explain about the interference pattern in thin films. And before I am going to derive the expression of interference pattern in thin films, that you all know that we have a number of colors of thin films. And suppose if you take the hard disk drives, compact disk, and such type of devices are linking with this particular concept of interference in thin films. We all know that the phenomena of interference patterns are observed that only one light, and let that light is called monochromatic light. To explain the phenomena of all interference patterns, we used a light called sodium vapor lamp. The other name for sodium vapor lamp is monochromatic light, whose wavelength of light is always 5893 angstrom units. If you want to convert this into centimeters, 1 angstrom unit is equal to 10 power minus 8 centimeters, and 1 angstrom unit is equal to 10 power minus 10 meters. So therefore, if you want to convert the wavelength of sodium light in centimeters, I can write it as lambda is equal to 5893 angstrom units. Okay. Now today I would like to explain the derivative part of interference pattern in thin films. This is exclusively coming under the geometrical analysis. Let us see with the beginning part of interference pattern in thin films. Okay. Now, the interference pattern in thin films is, the first topic is known as, I am writing here, interference pattern in thin films. To explain this, the other name for interference pattern in thin films, we simply call it as, the other name for it is cosine's law. Cosine's law or oblique incidence of a plane wave, oblique incidence of a plane wave in a thin film, of a plane wave in thin films. This is the other name for interference pattern in thin films. To explain this particular derivative part, my dear students, I would like to draw a diagram. See very carefully that I am going to take the two plane surfaces. Let this is called upper plane surface. I can call it as GH, and let this is called higher upper plane surface. GH is called upper plane surface and G1 H1 is called lower plane surface. A part of light ray, say AB, incident at a point B on upper plane surface GH, a part of light ray BR is reflected and a part of light ray BC is refracted. This is the first condition here. So a part of light ray AB strikes at a point B on upper plane surface GH, a part of light ray BR is reflected and a part of light ray BC is refracted. Is it clear? After getting one internal reflection at a point C, we get a ray CD and finally the ray DR1 emerges out in air. And I am going to write one normal from here to here like this. Now this is the angle of incidence, and draw two perpendiculars from B to CD, that is called BF. Draw a perpendicular BF on CD and draw another perpendicular DE on BR. This is called E. DE on BR by making an angle of incidence I, and this is the angle of incidence R. Now imagine that this is called rarer medium. The upper plane surface, the above portion of upper plane surface GH is called rarer medium, and we can take air as the best example. And the lower portion of G1 H1 is also considered as rarer medium. In between the upper plane surface GH and the lower plane surface G1 H1, we are calling it as denser medium. This we have to consider. This is called denser medium. That means I am considering that this is called film. My film is considered as denser medium. And again, my rarer medium is air medium. That is either sides of this particular upper plane surface and lower plane surface. Okay. Now, this particular thickness is considered as T from here to here, and similarly we consider thickness T from here to here. If you continue and draw the line from C to P like this is called P. I am considering it as, this is called Q, this is the angle of refraction R, and this is the angle of refraction R. Is it clear? Now, what I am taking here, I am writing everything here. Look at carefully. First of all, I am writing the derivative part here. Consider GH and G1H1 are the two plane surfaces, Let GH is the upper plane surface and let G1H1 be the lower plane surface. Consider a ray of light AB strikes at a point B on upper plane surface GH. What happens? A part of light ray BR is reflected, and a part of light ray BC is refracted. After getting one internal reflection, at a point D, we get a ray CD in film, and finally the ray DR1, and finally the ray DR1 here. This is called DR1. DR1 emerges out, ante bayadiki raavadam, emerges out in air. This is the explanation of the geometric analysis, what we have taken here, what are the terms that we have here taken here. Okay, I am repeating once again. Imagine that GH is the upper plane surface, G1H1 is the lower plane surface. Consider a part of light ray AB which strikes at a point B on upper plane surface GH. A part of light ray BR is reflected and a part of light ray BC is transmitted. After getting one internal reflection at a point C, we get a ray CD, and finally the ray DR1 emerges out in air. Okay. Now draw two perpendiculars. Say BF on CD, అంటే CD మీదకి BF అనే ఒక పర్పెండిక్యులర్ లైన్, అండ్ DE ఆన్ BR మీదకి DE అనేటువంటి ఒక పర్పెండిక్యులర్ లైన్ గీసాం. ఓకే, నౌ our ultimate article is to find out the optical path difference between the two reflected light rays. How to find that two reflected light rays optical path difference? I am writing here. Now, the optical path difference between the two reflected light rays What are those two light rays? We consider BR and DR1. BR and DR1. Now the optical path difference between the two reflected light rays BR and DR1 is given by, I am representing with delta, is given by delta is equal to mu into BC plus CD in film minus BE in air. If you look at that diagram, under students, I can consider it as equation 1. So BC plus CD existing in film and BE is in the air. Okay. Now, how to find this BE now? Look at carefully. To find BE. Okay. Now, to find BE, we consider two triangles. Say triangle. Look at carefully about this diagram so that you can understood here. Once again, I am telling you that if you see the diagram from triangle BDE and from triangle DBF, these two triangles we have to take here. From triangle BDE, we can write like this. From triangle BDE, sin I can write it as, we all know that the formula for sin I is opposite side by hypotenuse. Therefore, I can write it as BE by BD and from another triangle, triangle DBF. From triangle DBF, we can write sin R. That is like this. I will show that triangle here. From triangle DBF, if you find sin R from here, you know that formula FD by BD. FD is opposite side and BD is hypotenuse. Okay. So from triangle BDF, sin R I can write it as FD by BD. Bring both of them, and now I am going to using Snell's law. Mu is equal to sin I by sin R. Now I am substituting sin I and sin R in this above equation. I will get like this. Mu is equal to, what is sin I here? BI by D. BE by BD whole by, what is sin R here? FD by BD. If I write fractional mode, mu is equal to BE by BD into this, ఈ భిన్నం తిరగబడుతుంది, BD by FD. Okay. Now this BD cancel here. I will get mu is equal to BE by FD. Now again, substitute BE. Look at carefully here in the equation 1, mu into BC plus CD in film minus mu into BE in air. Okay. So therefore, what is mu in air? 1. Substitute mu in equation 1. We get delta is equal to mu into BC plus CD minus refractive index in air is always equal to 1. Therefore, I can get only BE here. So therefore, what is my BE here? If I take the cross multiplication, I can substitute like this. Followed by this, I am writing here BE, I can call it as equation 1, since mu is equal to 1 in air. అందువల్ల నాకు ఈక్వేషన్ 1లో mu is equal to mu in air ఎంత అవుతుంది? నాకు 1 అయిపోతుంది. సో అలాంటప్పుడు ఈక్వేషన్ 1 ఎలా రాసుకోవచ్చు నేను? డెల్టా ఈజ్ ఈక్వల్ టు mu into BC plus CD minus B. You have already determined the value of mu here. ఇప్పుడు mu is equal to BE by FDని నేను BEని ఎట్లా రాసుకోవచ్చు? క్రాస్ మల్టిప్లికేషన్ ద్వారా mu FDగా రాసుకోవచ్చు. అంటే ఇక్కడ రాస్తున్నాను చూడండి. దట్ ఇంప్లైస్ BE is equal to mu FD. Now I am substituting BE in this above equation. Now I am writing here, substitute BE in equation 2, we get delta is equal to mu into BC plus CD minus mu FD. Okay. Now coming to this diagram, my dear students, that in this equation I can write CD as, according to the properties of triangles, CD as CF plus FD. So I can write like this. Therefore delta is equal to mu into, every time this diagram is more important to continue this derivation. BC CD నేను ఎట్లా రాస్తున్నాను, CF plus FD గా రాశాను, minus mu FD. Okay, now again next step, మ్యూతో లోపల వాటిని మల్టిప్లై చేస్తున్నా, మ్యూ ఇంటూ బీసీ ప్లస్ సిఎఫ్ నేను ఇలా రాసుకొని ప్లస్ మ్యూ ఎఫ్డి, మ్యూ ఇంటూ ఎఫ్డి ఎంత, మ్యూ ఎఫ్డి మైనస్ మ్యూ ఎఫ్డి. ఇప్పుడు ఏం క్యాన్సిల్ అవుతాయి, ప్లస్ మ్యూ ఎఫ్డి మైనస్ మ్యూ ఎఫ్డి క్యాన్సిల్ అయిపోతే ఇంకేం మిగిలింది నాకు, డెల్టా ఈజ్ ఈక్వల్ టు మ్యూ ఇంటూ బీసీ ప్లస్ సిఎఫ్. కమింగ్ టు ద డయాగ్రామ్ అగైన్, ఇక్కడ నాకు సిఎఫ్, సి నుంచి ఎఫ్ చాలా జాగ్రత్తగా అబ్జర్వ్ చేస్తే బీసీ ప్లస్ సిఎఫ్లో బి నుంచి సి వరకు ఎంత డిస్టెన్స్ ఉందో, బి నుంచి సి వరకు ఎంత డిస్టెన్స్ ఉందో, పి నుంచి సి కూడా అంతే డిస్టెన్స్ ఉంటుంది. సో అకార్డింగ్ టు ద ప్రాపర్టీస్ ఆఫ్ ట్రయాంగిల్స్, హియర్ బీసీ ఈజ్ ప్యారలల్ టు పీసీ. ఓకే, therefore I can write instead of BC, I can write PC here. Therefore delta is equal to, the next step is like this, mu into PC plus CF. Since PC is parallel to BC, adi property of triangle. Okay, now again delta is equal to, coming to the diagram again, that ఇప్పుడు నాకు P నుంచి F ఉంది. How can I write like this? My PC plus CF. PC plus CF, I can write it as PF. Okay. So therefore I can change like this. Mu into PC plus CF నాకు ఎంత అవుతుంది? PF అవుతుంది. Okay. I can consider it as equation 3. The time we are going to get the expression for delta is equal to mu into PF, again we have to find PF. Okay. Now how to find PF? Again, to find PF, we consider a triangle. To find PF, we consider a triangle. Coming to the diagram, if you ఈ డయాగ్రామ్ కనుక మీరు చూసారనుకోండి, దీంట్లో ఇప్పుడు నేను పిఎఫ్ క్యాలిక్యులేట్ చేయాలి. పిఎఫ్ క్యాలిక్యులేట్ చేయాలంటే ఐ కెన్ కన్సిడర్ వన్ ట్రయాంగిల్, దట్ ఈస్ బీపీఎఫ్. ఓకే, బీపీఎఫ్. బీపీఎఫ్ నుంచి నేను ఎలా రాయొచ్చు, నేను కాసార్ టేకప్ చేశాను అనుకోండి, కాసార్ ఈజ్ ఈక్వల్ టు, ఇక్కడ నుంచి కాసార్ తీసుకుంటే అడ్జసెంట్ సైడ్ ఈజ్ పిఎఫ్ అండ్ హైపోటెనస్ ఈజ్ బీపీ. ఓకే, సో ఐ కెన్ రైట్ లైక్ దిస్. ఫ్రమ్ ఫిగర్ we consider from a triangle BPF, cos R is equal to PF by BP. And again from triangle, from diagram, we can write BP as, my students, BQ plus QP. Okay, BQ plus QP. So BQ is equal to how much? T. QP is equal to how much? T. Therefore again I can write like this, cos R is equal to PF by BQ plus QP. Okay, so in the diagram we consider BQ is T and QP is also T. Therefore I can write PF by T plus T. I can write it as cos R is equal to PF by T plus T, how much? 2T. Okay, 2T. T plus T, 2T. Now I am taking cross multiplication. PF is equal to, from this equation, PF is equal to 2T cos R. Okay, again already we have considered that in equation 3 delta is equal to mu into PF. Now substitute PF value in equation 3, we get delta is equal to mu into PF place లో ఇప్పుడు నేనేం పెట్టాలి, 2T cos R పెట్టాలి. Therefore delta is equal to, ఇదంతా ప్రొడక్ట్ కాబట్టి రీఅరేంజ్ లో ఇలా రాస్తాను, 2 mu T cos R. I can consider this as optical path difference between the two reflected light rays. I am giving a number which is called equation 4. Okay, so I am calling it as, which is the required expression for optical path difference between, which is the required expression for optical path difference between the two reflected light rays. This is our ultimate article would find out. In the beginning we have considered like this. Okay, but here according to phase change on reflection, what is this phase change on reflection is telling here? According to phase change on reflection, we also call it as Stokes theorem, or according to Stokes theorem, when a ray of light, I am writing statement here, Stokes theorem statement. According to Stokes theorem, when a ray of light is traveling from rarer medium to denser medium, it suffers an abrupt phase change. Abrupt ante sudden anamata. Abrupt phase change of pi radians or a path difference of plus or minus lambda by 4. This is all statement of Stokes theorem, my dear students. So I am repeating once again. According to phase change on reflection, the R Stokes theorem is telling that ఒక రే ఆఫ్ లైట్ ఎప్పుడైతే రేరర్ మీడియం నుంచి డెన్సర్ మీడియం ప్రయాణం చేస్తుందో, ఇట్ సఫర్స్ ఏ సడన్ ఫేజ్ చేంజ్ ఆఫ్ ఐదర్ పై రేడియన్స్ ఆర్ పాత్ డిఫరెన్స్ ఆఫ్ లాంబ్డా బై 4. మనకి ఈక్వేషన్ 4లో మనకి ఏమొచ్చింది? పాత్ డిఫరెన్స్ వచ్చింది. ఈక్వేషన్ 4 is telling exclusively that the optical path difference between two reflected light rays. సో therefore అలాంటప్పుడు నేను ఏం చేయాలి? ఈ 2 mu t cos r కి ప్లస్ ఆర్ మైనస్ లాంబ్డా 4 ని యాడ్ చేస్తా. అప్పుడు నాకు ఎఫెక్టివ్ ఆప్టికల్ పాత్ డిఫరెన్స్ వస్తుంది. therefore now the effective optical path difference is given by, now the effective optical path difference between these two reflected light rays is given by delta is equal to ఈ 2 mu t cos r కి ప్లస్ ఆర్ మైనస్ లాంబ్డా 4 ని కలపాలి. అంటే 2 mu t cos r ప్లస్ ఆర్ మైనస్ లాంబ్డా బై, దిస్ ఈస్ కాల్డ్ పై రేడియన్స్ ఆర్ ప్లస్ ఆర్ మైనస్ లాంబ్డా బై 2. ఓకే, 2 mu t cos r plus or minus lambda by 2. So I can consider it as equation 5. Delta is equal to 2 mu t cos r plus or minus lambda by 2 is called effective optical path difference. దీన్ని మనం షార్ట్ నోటేషన్లో UOPD అంటాం. Once again repeating here, fourth equation is called optical path difference and fifth equation is called effective optical path difference. Okay, 2 mu t cos r plus or minus lambda by 2. This is called plus or minus lambda by 2. అంటే ఫేజ్ డిఫరెన్స్ 5 ఉంటే పాత్ డిఫరెన్స్ లాంబ్డా బై 2 కి సమానం అవుతుంది. బికాస్ వీ హ్యావ్ రిలేషన్ బిట్వీన్ ఫేజ్ డిఫరెన్స్ ఈజ్ ఈక్వల్ టు 2 పై బై లాంబ్డా ఇంటూ పాత్ డిఫరెన్స్. ఓకే, సో విచ్ ఈస్ the required expression for effective optical path difference. Now when do we say that the film is appearing like look at carefully, after getting this expression for delta is equal to 2 mu t cos r plus r minus lambda by 2, my dear students, when do we say that this film is appearing like bright, and when do we say that the film is appearing like dark conditions? Okay, so we have two special cases to explain that the interference of thin films. When do we say that the film is behaving like bright film, and when do we say that the film is appearing or elevating like dark film? Let us see that both the conditions. Okay, now I am writing special cases. Special cases. The first case is condition for case 1. I am writing here case 1. Case 1, condition for bright film. This we can also call it as maximum intensity or constructive interference, like that. Condition for bright film. When do we say that the film is appearing like a bright film? That's what I am saying now. Condition for bright film. If the optical path difference between the two reflected light rays delta is equal to, if delta is equal to n lambda, what is n lambda here? N is called integral multiples of wavelength lambda. But we know that from equation 5, we have delta is equal to మనకి ఎంత వచ్చింది ఈక్వేషన్ 5లో 2 mu t cos r ప్లస్ ఆర్ మైనస్ లాంబ్డా బై 2 వచ్చింది. ఇప్పుడు ఈ రెండింటిని సమానం చేస్తే ఈక్వేటింగ్ బోత్ ఆఫ్ దెమ్ 2 mu t cos r ప్లస్ ఆర్ మైనస్ లాంబ్డా బై 2 ఈజ్ ఈక్వల్ టు n లాంబ్డా అయితే ప్లస్ ఆర్ మైనస్ లాంబ్డా బై 2 రైట్ హ్యాండ్ సైడ్ తీసుకెళ్ళాం అనుకోండి, అప్పుడు సింప్లిఫై చేస్తే 2 mu t cos r ఈజ్ ఈక్వల్ టు n lambda plus or minus lambda by 2. Now 2 mu t cos r is equal to right hand side LCM కట్టాం అనుకోండి ఫర్ ఎగ్జాంపుల్, అప్పుడు ఎంత వస్తుంది మనకి? ఇఫ్ ఐ టేక్ LCM 2 హియర్ 2n lambda plus or minus lambda. ఓకే, సింప్లిఫై చేసాం అనుకోండి నెక్స్ట్ స్టెప్లో 2 mu t cos r is equal to, దిస్ ఈజ్ a plus r minus b by 2 రూపంలో ఉంది కాబట్టి 2n lambda by 2 plus or minus lambda by 2. దీనిలో కామన్ తీసాం అనుకోండి, ఇప్పుడు ఏమొస్తుంది మనకి? 2 mu t cos r is equal to 2n plus or minus 1 into lambda by 2 వస్తుంది. ఓకే, సో దిస్ ఈస్ ద అల్టిమేట్ ఎక్స్ప్రెషన్ ఫర్ కండిషన్ ఫర్ బ్రైట్ ఫిల్మ్. సో ఐఎమ్ రైటింగ్ కామెంట్ హియర్. వాట్ ఈస్ దట్ కామెంట్? యు నో, ఇఫ్ దిస్ కండిషన్ ఈజ్ ఫుల్ఫిల్డ్, if this condition is fulfilled, then the film will appears as bright. Similarly, case 2 ఏం చెప్తుందంటే కండిషన్ ఫర్ డార్క్ ఫిల్మ్కి వెళ్దాం. Condition for dark film. When do we say that the film is appearing like dark film? Okay. Now, if delta is equal to 2n plus or minus 1 into lambda by 2, odd number multiples of wavelength lambda by 2 అంటాం దీన్ని మనం. But we know that from equation 5, first case లాగే, but we know that from equation 5 we have delta is equal to 2 mu t cos r plus or minus lambda by 2. ఇప్పుడు ఈ రెండింటిని సమానం చేయాలి. చేసామనుకోండి ఎంత వస్తుంది? 2 mu t cos r plus or minus lambda by 2 is equal to 2n plus or minus 1 into lambda by 2. ఓకే, నా ఇప్పుడు ప్లస్ ఆర్ మైనస్ lambda by 2 రైట్ హ్యాండ్ సైడ్ తీసుకెళ్తే 2 mu t cos r is equal to 2n plus or minus 1 into lambda by 2 plus or minus lambda by 2. దీన్ని మనం సింప్లిఫై చేసాం అనుకోండి, ఎట్లా సింప్లిఫై చేయాలి? ఇక్కడ ప్లస్ తీసుకుంటే ఇక్కడ మైనస్ తీసుకోవాలి. ఓకే, సో నేను రాస్తాను స్టెప్ 2n ప్లస్ లాంబ్డా ప్లస్ 1 ఇంటూ లాంబ్డా బై 2 మైనస్ లాంబ్డా బై 2. సింప్లిఫై చేసాం అనుకోండి 2 mu t cos r is equal to 2n ప్లస్ 1 ఇంటూ లాంబ్డా బై 2 ఒక స్టెప్, మైనస్ లాంబ్డా బై 2 ఒక స్టెప్. నేను సింప్లిఫై చేస్తే ఎంత వస్తుంది? 2 mu t cos r is equal to 2n ఇంటూ లాంబ్డా బై 2 ఒక స్టెప్, ప్లస్ లాంబ్డా బై 2 మైనస్ లాంబ్డా బై 2. ప్లస్ లాంబ్డా బై 2 మైనస్ లాంబ్డా బై 2 క్యాన్సిల్ అయిపోతాయి, 2 క్యాన్సిల్ అయిపోతాయి. నాకేం మిగిలింది, 2 mu t cos r is equal to n lambda మిగులుతుంది. దిస్ ఈజ్ ద కండిషన్ ఫర్ డార్క్ ఫిల్మ్. ఇక్కడ కామెంట్ రాస్తున్నాను, ఏంటది, ఇఫ్ దిస్ కండిషన్ ఈజ్ ఫుల్ఫిల్డ్, if this condition is fulfilled, then the film will appear as dark. Film will appear as dark. Okay, this is the methodology of finding a condition for bright film and condition for dark film. Okay, so in the beginning onwards, what you have understood, my dear students, strictly speaking, that interference pattern observed in thin films. Okay, this we also call it as cosine's law, because in the equation 4 we have got that delta is equal to mu t cos r, and equation 4 we are exclusively calling it as effective optical path difference between the two reflected light rays, and according to Stokes theorem, and that Stokes theorem we also call it as phase change on reflection. According to this theorem, when a ray of light is traveling from a rarer medium to denser medium, it suffers an abrupt phase change of pi radians or a path difference of plus or minus lambda by 2. Therefore, in equation 4 we have got the optical path difference between the two reflected light rays, that is delta is equal to mu t cos r. I just add this plus or minus lambda by 2 to that 2 mu t cos r. I could write delta is equal to mu t cos r plus or minus lambda by 2, and that equation is 5, and that equation 5 I am calling it as effective optical path difference. Is it clear? So when delta is equal to n lambda, my film is behaving like a bright film, and if delta is equal to 2n plus or minus 1 into lambda by 2, so what's the meaning of that? Let me tell you first of all. Delta is equal to n lambda అంటే ఆప్టికల్ పాత్ డిఫరెన్స్ న్యాచురల్ నంబర్స్ ఆఫ్ వేవ్ లెంగ్త్ లాంబ్డాకి సమానం అయినప్పుడు ఈ 2 mu t cos r plus or minus lambda by 2 ని n లాంబ్డాకి సమానం చేసి సింప్లిఫై చేస్తే we have got delta is equal to, మనకి ఎంత వచ్చినప్పుడు ఫైనల్గా 2 mu t cos r is equal to 2n plus or minus 1 into lambda by 2 వచ్చింది. ఓకే, అలాగే అప్పుడు మనకు బ్రైట్ కండిషన్ ఫుల్ఫిల్ అయింది అనమాట. అట్లాగే డెల్టా ఈజ్ ఈక్వల్ టు 2n plus or minus 1 into lambda by 2 అంటే ఆడ్ నెంబర్ మల్టిపుల్స్ ఆఫ్ వేవ్ లెంగ్త్ lambda by 2 కానీ, లేకపోతే ఈవెన్ నెంబర్ మల్టిపుల్స్ ఆఫ్ అక్కడ పాజిటివ్ ఆడ్ నెంబర్ కానీ నెగిటివ్ ఆడ్ నెంబర్ కానీ జాగ్రత్త గుర్తుపెట్టుకోవాలి. డెల్టా ఈజ్ ఈక్వల్ 2n plus or minus 1 into lambda by 2లో రెండు ఉన్నాయి మనకి. 2n plus 1 into lambda by 2 అయితే ఆడ్ నెంబర్ మల్టిపుల్స్ ఆఫ్ వేవ్ లెంగ్త్ lambda by 2 అంటాం. 2n minus 1 into lambda by 2 అయితే నెగిటివ్ ఆడ్ నెంబర్ ఆఫ్ మల్టిపుల్స్ వేవ్ లెంగ్త్ అంటాం. సో దేర్ ఫోర్ ఇఫ్ డెల్టా ఈజ్ ఈక్వల్ 2n plus or minus 1 into lambda by 2 and we equate it to that 2 mu t cos r plus or minus lambda by 2, అలా చేస్తే మనకేమొచ్చిందంటే ఫైనల్గా 2 mu t cos r is equal to ఎంత వచ్చింది, n lambda వచ్చింది. ఓకే, సో దిస్ కండిషన్ ఈజ్ కాల్డ్ కండిషన్ ఫర్ డార్క్ ఫిల్మ్. ఇఫ్ దిస్ కండిషన్ ఈజ్ ఫుల్ఫిల్డ్, ద కండిషన్ we are calling it as dark film. Is it clear? So therefore interference pattern thin films లో రెండు కేసెస్ ఉంటాయి. ఏంటా రెండు కేసెస్ అంటే కండిషన్ ఫర్ బ్రైట్ ఫిల్మ్, కండిషన్ ఫర్ డార్క్ ఫిల్మ్. After finishing this, my dear students, I would like to enter into the theory of interference fringes. Okay, the next subsequent topic is, my dear students, theory of interference fringes. Theory of interference fringes. Before I am going to explain the theory of interference fringes, we have one experiment which is called Young's double slit experiment. Let me complete this Young's double slit experiment, and then you can understood the mathematical part of theory of interference fringes. Young's double slit experiment. I am going to draw the diagram like this. Imagine that this is called source of light, and I have two narrow pinholes. They are called S1 and S2. This is called XY. This XY is called screen. Thomas Seng demonstrated that let S is the source of monochromatic light, and the wavelets that are coming out from the source of light is like this. This is called circular arc, and I can call it as wave crest. This is called dotted circular arc. I can name it as wave trough, and one crest and one trough, wave trough is producing like this. Okay, and these S1 and S2 are called the two narrow pinholes. Is it clear? Imagine that this particular portion is called opaque slit width. The light did not enter through this. Okay, this is called opaque slit width. Again, even after passing through these two slits S1 and S2, again the first wavelet is coming in the form of circular arc like this. Here also circular arc, and again dotted circular arc is producing like this. Dotted circular arc is producing like this. Again one wave crest and one wave crest like this. After producing like this, my dear students, in between the two narrow pinholes S1, S2 to the screen XY, there are three possibilities of getting interference pattern produces. How you know? S1 అనేటువంటి narrow pinhole గుండా వచ్చినటువంటి ఒక వేవ్ క్రెస్ట్ నాకు S2 నుంచి వచ్చినటువంటి ఎనీ వేవ్ క్రష్తో కనుక ఓవర్లాప్ అయితే దట్ ఈస్ కాల్డ్ కన్స్ట్రక్టివ్ ఇంటర్ఫరెన్స్. అలాగే S1 నుంచి వచ్చినటువంటి వేవ్ ట్రఫ్ డాటెడ్ సర్క్యులర్ ఆర్క్కి మనం ఇచ్చిన పేరు వేవ్ ట్రఫ్. S2 నుంచి వచ్చినటువంటి ఇంకొక వేవ్ ట్రఫ్తో కనుక ఓవర్లాప్ అయితే దాన్ని కూడా కన్స్ట్రక్టివ్ ఇంటర్ఫరెన్స్ అని అంటాము. అలాగే S1 అనేటువంటి నేరో పిన్హోల్గా వచ్చినటువంటి వేవ్ క్రస్ట్, ఎనీ వేవ్ క్రస్ట్ which is ready to overlap with any other wave crest coming from the pinhole S2, we are calling it as destructive interference. Is it clear? So this is what is known as the Young's double slit experiment is telling, and the pattern is producing like this. One wave crest is coming like this and another wave crest is overlapping like this. So there are three possibilities. Is it clear? Now I am writing here, let S is called source of light. Let S is a source of monochromatic light. Let us is a source of monochromatic light. Monochromatic light, and let S1 and S2 are the, let S1 and S2 are the two narrow pinholes. Let S1 and S2 are the two narrow pinholes. Let XY is the screen. Let XY is the screen. What happening we are observing on that screen. Let this representation of, this is called circular arc. Circular arc. We are calling it as wave crest. And this is called dotted circular arc. We are calling it as dotted circular arc. I can name it as wave trough. Wave trough. Okay. Now to get the interference pattern, we have three possibilities, my dear students. So what are three possibilities here? Okay, I would like to explain first of all. In Young's double slit experiment, my dear students, what exactly Young's double slit experiment is telling here? S is a source of monochromatic light. The light rays that are delivered from the source of monochromatic light is in the form of continuous circular arc and dotted circular arcs. Okay. Circular arc is named as wave crest and dotted circular arc is named as wave trough. Okay. There are three possibilities of getting interference pattern, that S1 అనేటువంటి narrow pinhole గుండా వచ్చినటువంటి ఏ వేవ్ క్రస్ట్ అయినా S2 నుంచి బయటకు వచ్చినటువంటి ఎనీ వేవ్ క్రస్ట్తో ఓవర్లాప్ జరిగితే దాన్ని కన్స్ట్రక్టివ్ ఇంటర్ఫరెన్స్గా పరిగణిస్తాం. దట్ ఈస్ ద ఫస్ట్ పాసిబిలిటీ ఆఫ్ గెటింగ్ ఇంటర్ఫరెన్స్ ప్యాటర్న్. దట్ ఈస్ కాల్డ్ కన్స్ట్రక్టివ్ ఇంటర్ఫరెన్స్ ప్యాటర్న్. ఓకే. అలాగే S1 అనేటువంటి నేరో పిన్ హోల్ నుంచి వచ్చినటువంటి ఏ వేవ్ ట్రఫ్ అయినా S2 నుంచి వచ్చినటువంటి ఎనీ వేవ్ ట్రఫ్తోనైనా సరే ఓవర్లాపింగ్ జరిగితే దట్ ఈస్ కాల్డ్ also constructive interference, and that means there are two possibilities of receiving constructive interference. Okay, crest to crest overlapping aina constructive interference antam, trough to trough overlapping aina kuda constructive interference antam. Ala gaakunda S1 అనేటువంటి narrow pinhole నుంచి వచ్చినటువంటి ఎనీ వేవ్ క్రస్ట్ S2 నుంచి వచ్చినటువంటి ఎనీ వేవ్ ట్రఫ్ తో ఓవర్లాపింగ్ జరిగితే దట్ ఈస్ కాల్డ్ destructive interference pattern antam. Okay, now I am writing, you look at carefully. So the first possibility I am writing here, first possibility, number one. ఏంటి ఆ ఫస్ట్ పాసిబిలిటీ అంటే If a wave crest, I am writing like this so that you could understand. If a wave crest coming from the pinhole S1 ready to overlap with any other wave crest coming from the pinhole S2 is called constructive interference pattern. Okay, constructive interference pattern. This is the first possibility of getting constructive interference. Is it clear? The second one is, if a wave crest, I am underlining here, look at carefully that if a wave crest coming from the pinhole S1 ready to overlap with any other wave crest coming from the pinhole S2. Is it clear? Similarly, if a wave trough coming from the pinhole S1 ready to overlap with any other wave trough, understood carefully, any other wave trough coming from the pinhole S2 is called also constructive interference. Okay, I am underlining with red pen now so that you can understood here. Look at carefully. If a wave trough coming from the pinhole S1 ready to overlap with any other wave trough coming from the pinhole S2. Is it clear? This is what is known as constructive interference. So therefore, there are two possibilities of getting a constructive interference. Whereas the third one is represented like this. Look at carefully. The third possibility is, if a wave crest coming from the pinhole, S1 ready to overlap with any other wave trough. This you have to understood. Any other wave trough coming from the pinhole S2, then it is called destructive interference pattern. Destructive interference, full stop. Is it clear? So, strictly speaking that, my dear students, you could understood that the first one is known as, okay, if you see the first one, there are three possibilities. Out of three possibilities, the first two possibilities are giving constructive interference and the third possibility is giving destructive interference. Okay, so I am repeating once again. If a wave crest coming from the pinhole S1 ready to overlap with any other wave crest coming from the pinhole S2, it is called constructive interference pattern. And if a wave trough coming from the pinhole S1 ready to overlap with any other wave trough coming from the pinhole S2 is also termed as constructive interference pattern. Whereas if a wave crest coming from the pinhole S1 ready to overlap with any other wave trough coming from the pinhole S2, we are calling it as destructive interference pattern. Is it clear? So therefore, with this, my dear students, we have completed Young's double slit experiment, and based on this Young's double slit experiment, how to find the fringe width, and what is the condition for bright fringe, and what are the conditions for dark fringe, by uses of theory of interference fringes. Let us derive it in the next class. Thank you very much. Okay.